So what is the rule? Not adding, for sure. Now, I don't remember, like, ever in my career hearing before that, oh, we must subtract them. And I heard it 3 times today. I mean, I think that's a good thing, because I think that means that you guys are, like, comfortable enough to just blurt out, like, your first thought about something. So I actually kind of see that as a good sign. But it's wrong. And I think all 3 of you that blurted that out kind of realized it once you actually did the mental math. So it is not true, certainly not true that we add them. And it's not true that we subtract them either. But what I think every group found, and correct me if I'm wrong, is that your combined resistance was less than either of your individual resistors. Were there any violations of that? Is there anybody whose total resistance was more than your smaller resistance? No. Alright, is that weird? I think it's a little weird. I think it's a little weird at first glance. But actually, when we remember what we've already said about parallel circuits, it's not so weird. It's not so weird. I don't know why I erased. I should have erased. So we all had 2 resistors that were connected in parallel, and our definition of resistance is just the ratio of the potential difference to the current. I mean, that is the physics definition of electrical resistance. And if we're talking about the total resistance, we would also need to talk about the source potential difference and the total current. So how does the source potential difference compare to the branch voltage drops? It's the same. All right, so what I want to do is compare this resistance to one of the individual resistances, which is the individual voltage drop divided by the individual current. So Will is right. The source potential difference is exactly the same as each branch's voltage drop. But what about the total current? How does the total current compare to an individual branch current? We just said this 3 minutes ago. The total current is more, because we have to add the individual currents together, right? And that gives us the total current. So the total current in the circuit is greater than any individual current. So even though the numerators are the same, the denominator for the total resistance is larger than the denominator for the individual resistance. So of course the total resistance is smaller, because the circuit as a whole is drawing more current than either of our individual branches. So it actually makes complete sense that the combined resistance of a parallel circuit is less than any of the individual resistances. Okay? So again, as we add not just a second branch, but as we add more and more and more and more branches, the overall resistance of the circuit continues to decrease, because as we add more branches, we're drawing more and more and more current from the battery. Give 10 seconds for that to sink in a little bit. Questions about parallel circuit, the total resistance decreases as we add more and more and more parallel branches. Yes?
Is this where the battery comes in?
Absolutely, because we're drawing more current out of the battery. We're delivering more charges from the battery in a given amount of time. So absolutely it wears it out. It uses it up faster, sure. Okay. Now, so how do we do it? I mean, there must be a way to find the total resistance. And it actually is just addition, but it's addition of the inverse of the resistances, okay? So 1 over the total resistance equals 1 over the individual resistances added together. Right, and that is on your equation sheet, but it's not labeled as parallel, right? Both of the resistance expressions for series and parallel are there, but you need to know which is which. And just a word of warning before we go ahead and solve the parallel circuit problem together. I tend to always have a few students that will successfully add these together, but then not take the last step. Once we add those together, that gives us the inverse of the total resistance. We aren't looking for the inverse of the total resistance. We almost always want to find the resistance itself. So please be careful. Once you do the right-hand side, you still have one more step to do to get the total resistance. All right, so just like for series circuits, I can offer you a typical sequence for solving parallel circuit problems, but I don't promise that we always do these steps in this exact order. So when we're trying to evaluate a parallel circuit, we do typically find the total resistance of the circuit first. And then we typically find the total current in the circuit. And remember, all we need to do any of these things besides find the total resistance is use Ohm's law. But if we want to find the total current, then we do need to use the total resistance. And then once we find the total current, we would typically be interested in finding the individual branch currents. And if we want to find an individual branch current, like maybe for branch 2, then we would have to use the resistance of just branch 2. All right, so let's do it, right? If we don't start now, we're not going to be able to comfortably complete this whole thing. So we're going to have a pretty, actually not that simple of a parallel circuit, more complicated than the ones that we built today, because we have 3 resistors, right? We have 12.4 volts worth of batteries, so maybe we have a car battery, maybe we have 2 lantern batteries, and we have 3 pretty moderate resistors. We want to find everything that we can possibly find. What am I going to do first? I'm going to draw the darn circuit, right? I'm going to try to use correct symbols and rules for circuit diagrams. So here's the battery, and I need 3 different branches that have 1 resistor each on them. All right, so I have 12.4 volts, so I'm just going to label that next to my battery, and then I'll label the resistances next to the resistors. And it makes no difference what order you draw them in, right? It makes no difference at all. I'm just going to do them in the order that they were given in the problem, but if you want to be different, you can do it different. All right, so first we want to find the total resistance of the circuit. So we get to use our new parallel resistance expression, but I do need 3 terms, since I have 3 resistors. All right, so I have 1 over 56, and 1 over 72, and 1 over 95. Now, what is your math teacher going to want you to do there? Your math teacher probably not only wants a common denominator, but they probably want the least common denominator. I couldn't care less about any common denominator, let alone the least common denominator. In fact, especially in the interest of time, since we only have 10.5 minutes, I'm just going to let my calculator do that lifting for me. Now, I better get an answer that's less than 56. The total resistance has to be less than even the smallest individual resistor. And I'm getting, for the combination of those 3 fractions, 0.0422723 other stuff. Can anybody confirm that? Fantastic. And then I don't want that, though. I want the inverse of that, right? Because that's equal to the inverse of the total resistance. So again, I'm going to let my calculator do the lifting here, and I'm going to, for the first time in this course, I'm going to use my x to the negative 1 button, right, to give me the inverse of that. If you don't have an x to the negative 1 button, or you don't like doing that, then just do 1 divided by 0.0422725. And I get something that looks like 23.656. Right, so let me pause there as we think about significant digits on that. While we're thinking about significant digits, though, we will appreciate that this is less than my smallest individual resistor, which is good. All right, what's it going to be? It is going to be 24Y. Yes. So this equation is adding. I'm adding 3 terms together to get another term. I'm going to use my adding rule. Coincidentally, for this problem, if I use my multiplying and dividing rule, I would still have 24. But I'm saying I have 24 because each of these had a 1's place. Alright, so the total resistance of this circuit is 24 ohms. Follow-up issues from anybody about finding the first thing we're looking for. Okay, the second thing we're looking for is the easiest thing we could possibly be asked to find. Find the electric potential difference across each resistor. So we want the voltage drop of the 56 ohm resistor, we want the voltage drop of the 72 ohm resistor, and we want the voltage drop of the 95 ohm resistor. And what are they? 12.4 volts, because every branch gets the full potential difference of the power supply. And I do not need to show any work for that at all. Okay, so that is the majorly important thing about parallel circuits, is that each branch gets the full potential difference of the power source. Follow-up questions about that? All right, next, find the total current in the circuit. All right, so the total current, we would use Ohm's law for this. And if I manipulate Ohm's law to solve for current, I get delta V over R. If I want the total current, I do use the source voltage, but actually that's fine, because the potential difference for everything is the same. And if I want the total current, I am going to use the total resistance. Alright, so the total current should be my 12.4 volts divided by 23.656 ohms. I want to use my unrounded version. It's going to be what? It's going to be a little more than a half. Yeah, 0. And I should keep extra digits because I'm going to use this again. 0.5242 is probably good enough. I mean, my actual answer to this part is 0.52 amperes. But looking ahead, I know I'm using that to find other stuff. Alright, follow-up questions on finding that the total current is 520 milliamperes. 0.52 amperes is 520 milliamperes. That's a lot. Alright, next, find the current through each resistor. I'm going to cheat, and I'm just going to find the current through one of the resistors because I would use the exact same process to find the other ones. Anybody have a favorite that you want us to find?
72.
Alright, 72 it is. Wow. So the current through this, well, the current, we always use Ohm's law. We've already rearranged Ohm's law to solve for current, and it's delta V over R. And if we want to find the current through the 72 ohm resistor, then we better use the voltage drop of just the 72 ohm resistor, and we better use the resistance of just the 72 ohm resistor. So the voltage drop of the 72 ohm resistor was 12.4 volts. Everybody's getting the full 12.4 volts. And then the resistance of the 72 ohm resistor is just 72 ohms. And I'm actually not going to end up using this for anything else, because we're only after this looking for the total, oh no, the power for each resistor. So yeah, I do need to use this for something else. So let me keep some extra digits, and then I'll rewrite it to the correct number of significant digits, 0.17 amperes. And that better be less than the total current in the circuit, and it is less. Follow-up questions about finding the current in an individual branch. Alright, finally, we want to find the power dissipated by each resistor, but we're just going to do that through the 72 ohm resistor, right? So we know that power is current multiplied by potential difference. If we want the power of just the 72 ohm resistor, then we need to use the current of just the 72 ohm resistor as well as its voltage drop. So the current is what we just found, 0.1722, and then the voltage drop was the 12.4 volts. Everybody's getting 12.4 volts. and I'm getting less, dude. I'm getting something like 2.1 watts. It's not actually very powerful. Would it be what? No, because the current was actually rounded to 2 significant digits. I was just keeping extra digits there. Other issues about finding the power of an individual branch. What about the total power? What would we do for that? Total current. The total power, we would use the total current. That's right. All right. So you will be doing at least one problem very similar to that. I want to do one other thing in our remaining 2.5 minutes, and it involves our light bulb. So since I burned our light bulb out, I need to go get a new one. Can you guys please disconnect your wires from your resistors and then loop the end of the wire to the other end? Yes.
You gonna throw this one out?
Yes, please. Oh, I put my batteries away too. Okay. How many batteries were good for these light bulbs that we're using? Anybody remember? I think it was 2, right? So what I'd like to do is re-hook up one of these light bulbs to the 3 volts worth of batteries. And hopefully you're sitting in some place where you can kind of see the light bulb. Now, did we hook up the second light bulb in series with this one earlier?
Yes.
Well, we did, but not with the 2 batteries, I don't think. So when I hook up the second light bulb in series with this one, what should happen to the brightness of this one? Same, huh? I think it's going to be less bright. In series, I think it's going to be less bright because we're going to have less current and a smaller voltage drop, right? Because I'm adding more resistance to the circuit if I hook up a second light bulb. So let's make sure that that's true. What do I need to do? I think I need to unattach this one here, that one in series. It's way dimmer, right? Way dimmer. Again, we added extra resistance to the circuit, so less current, and they're splitting the potential difference of the batteries. What? So let me give you 5 seconds to think about that. What if I connect this other light bulb in parallel to the first one? It should be the same. Now, in reality, because of the resistance of the wires, things might change slightly, but it should be pretty much, yeah. I'm not sure that I noticed a difference in it. Little tiny difference. Yeah, so and again, in parallel, each branch is getting the full potential difference of the batteries, and the current is only determined by the resistance of the branch itself.